So in today's video, we're going to be talking about free radical damage. By the time this video ends, you should understand what free radicals are, how do free radicals cause damage, sources of free radicals, neutralization, clinical relevance, and then we're going to go ahead and practice some USMLE practice questions to solidify your knowledge for the long term. Be sure to check out the healingpowerofnature.com and also our Patreon for exclusive content and the best materials on the market to make medical school as easy as possible. So to start, the definition of free radicals. So free radicals are molecules or atoms with an unpaired electron in their outer shell. This makes them highly unstable and reactive, seeking to stabilize by stealing electrons from nearby molecules. This leads to oxidative damage. So some etymology. So the word free means not bound or constrained. So these molecules act independently, causing widespread damage. Radical, from the Latin root radix, means root. This highlights their role as the root cause of damage. So how do free radicals cause damage? Free radicals inflict damage through three main mechanisms. The first is lipid peroxidation. Free radicals attack polyunsaturated fatty acids in the cell membrane. As we know, cell membranes are composed of fats, so this creates lipid peroxides, which comprise membrane integrity. Some examples of this are acetaminophen toxicity, so metabolized in the liver by NAPQI, a free radical, causing lipid peroxidation and hepatocyte necrosis. A mnemonic you can think of is lipids are like balloons, radicals pop them, okay? Another one is protein modification, so free radicals modify proteins, causing misfolding and loss of function. Some examples can be Parkinson's disease, for example. Oxidative stress contributes to formation of Lewy bodies. So some clinical correlations, so neurodegenerative disorders often involve free radical damage to proteins. Proteins lose their shape under stress. And lastly, you're going to have DNA damage, so free radicals cause single and double-stranded DNA breaks, mutations, or even apoptosis. Some examples are radiation therapy, so killing cancer cells by generating free radicals. This can also cause double-stranded DNA breaks. So clinical correlation is that free radicals or radiation therapy increases the cancer risk or secondary malignancy. Remember, radicals rip the DNA zip. Sources of free radicals, so we have both endogenous and exogenous sources. So endogenous sources, sources of free radicals within the human body include mitochondrial oxidative phosphorylation. Remember, in the electron transport chain, the ETC produces superoxide as a byproduct. This is detoxified by enzymes like superoxide dismutase. We also have inflammation. So NADPH oxidase generates free radicals during oxidative bursts to kill pathogens. So chronic inflammation is sustained oxidative damage. Some exogenous sources, so pathological generation of free radicals. Free radicals can also form abnormally in the body due to specific triggers. So ionizing radiation, like we talked about, so high energy radiation like X-rays, gamma rays, actually split water molecules into hydroxyl free radicals, or OH. Examples would include radiation therapy, so cancer treatment generates free radicals to kill tumor cells, but it can also damage normal tissue like skin or mucosa. Remember, radiation rips water apart. Additionally, inflammation again. So during infection, NADPH oxidase in neutrophils generates superoxide radicals for pathogen killing. So superoxide is further converted into more reactive species like hydrogen peroxide and hydroxyl radicals. Remember, hydroxyl radicals are the most potent. It's basically bleach. Some examples are chronic inflammation. Conditions like rheumatoid arthritis lead to sustained RRS production, contributing to tissue damage. Additionally, metal reactions, so free iron, Fe2, or copper, Cu2, catalyzes the Fenton reaction. So examples of this are hemochromatosis, so excess iron deposition in tissues, like the liver or the heart, catalyzes radical formation, leading to fibrosis and organ damage. Also, Wilson's disease, copper accumulation causes oxidative stress and cell injury. Remember, iron and copper feed radicals. Drugs and chemicals. The liver's cytochrome P450 enzyme system metabolizes drugs, producing free radicals as a byproduct. So a common example you'll see is acetaminophen overdose. Excessive metabolism forms NAPQI, a highly reactive free radical that depletes glutathione and causes hepatocyte necrosis. Also, carbon tetrachloride, CCl4, metabolized into radicals leading to fatty liver and central lobular necrosis. This was actually originally seen with dry cleaning, but P450 pathway produces problems, okay? Now, the neutralization of free radicals. So the body employs antioxidants and enzymes to detoxify free radicals. So enzymes you need to know about. Superoxide dismutase converts superoxide O2 into H2O2. Also, catalase converts H2O2 into harmless H2O and O2. Additionally, glutathione peroxidase uses glutathione to detoxify H2O2 and other radicals. Some antioxidants you need to be aware of: vitamin C and vitamin E. Vitamin C is water soluble, so it scavenges free radicals in the plasma. Vitamin E is lipid soluble, protects membranes from lipid peroxidation. Additionally, glutathione, central antioxidant in cells. A mnemonic you can remember: so cool, so great. S, superoxide dismutase. C, catalase. G, glutathione peroxidase. Remember, S, superoxide dismutase converts superoxide into H2O2. Catalase converts H2O2 into harmless H2O and O2. Glutathione peroxidase, what does that do? It reduces glutathione to detoxify H2O2 and other radicals. Clinical relevance that you need to know about. So remember, carbon tetrachloride cracks liver cells. That's one way you can think about it. Also, remember reperfusion injury. So after ischemia, restored oxygen flow generates ROS, worsening injury. Why is that? So if you have a tissue that hasn't had any sort of blood flow or oxygen delivering the system, it's going to have a reperfusion. That rapid increase in the electron transport chain will deliver reactive oxygen species. So post-MI damage, post-myocardial infarction damage, exacerbated by reperfusion. Another example, hemochromatosis and Wilson's disease. So iron catalyzes free radical generation in the Fenton reaction. So in Wilson's disease as well, excess copper is oxidative stress. Iron and copper feed free radicals. Also, radiation therapy generates free radicals to damage cancer cells but can also harm normal tissues in the process, causing secondary malignancy. Parkinson's disease. Oxidative stress contributes to the formation of Lewis bodies. Additional examples for practice that might show up on tests and also in clinic: ALS, amyotrophic lateral sclerosis. So mutations in SOD1 lead to accumulation of RRS, motor neuron death. Also, age-related macular degeneration, AMD. Oxidative damage contributes to central vision loss. Some key takeaways to make this a little bit easier. Remember, free radicals damage lipids, proteins, and DNA, leading to diseases like cancer, neurodegeneration, and ischemic injury. The body fights back with antioxidants, vitamin C and E, and enzymes like catalase, glutathione peroxidase, and SOD. Pathologic free radicals arise from radiation, inflammation, metals, and drugs. Damage occurs via lipid peroxidation, DNA mutations, and protein dysfunction. Neutralization relies on antioxidants and enzymes. A mnemonic you can use for free radical damage: lipid, DNA, protein. Radicals damage them all. A mnemonic you can use is radio. So, for example, when I think of radiation, I automatically think of radio. Why? Because it tells me what causes the problem. R for radiation, A for activated neutrophils, D for drugs, I for iron, O for oxygen and oxidative phosphorylation. Now, let's go through a few USMLE practice questions. Like I always will tell you, start by reading the last sentence, then read your answer choices, then read the entire question. So I'll go ahead and give you a few minutes, and then we'll go over and review this question together. Okay, so the correct answer was B, formation of hydroxyl free radicals. Remember, ionizing radiation, for example, X-rays or gamma rays, damages tissues primarily by splitting water molecules, H2O, to generate hydroxyl free radicals, OH, which causes oxidative DNA damage and cell death. This mechanism explains why radiation therapy can injure normal tissues along with normal tumor cells. Let's go ahead and do another question. I'll give you a few minutes and then we'll come back and review together. So if you chose C, free radical generation and lipid peroxidation, you are correct. So remember, acetaminophen overdose leads to the excessive production of NAPQI, a highly reactive free radical that depletes glutathione and causes lipid peroxidation, leading to hepatocyte necrosis. So let's do one more practice question. I'll give you a few minutes, then we'll come back and review together. So if you chose B, free radical formation from oxygen reintroduction, that is correct. Remember, reperfusion injury occurs when oxygen is suddenly reintroduced to ischemic tissues, generating reactive oxygen species such as superoxide, hydrogen peroxide, and hydroxyl radicals. These free radicals cause lipid peroxidation, protein oxidation, and DNA damage, leading to further tissue injury despite restored blood flow. This is due to the electron transport chain and how it naturally produces free radicals as a byproduct. So that concludes our video for today. If this video was confusing to you, that is completely normal. I recommend watching it several times and also checking out thehealingpowerofnature.com for our book and also complete study guides that make this material as easy as humanly possible. Thank you again, and I'll see you next time.